All right, yeah, so welcome again. This is the second, regional Northeast Ohio quantum meetup. We're really excited to have everyone here. As you probably saw and heard, we are started recording, and we will make this available online on YouTube at our channel, and we'll pass links to that through the different invite sources and on our main meetup page. But we're really excited to have everyone here. We'll have speakers from D-Wave and Zapata. And if you want to go to the next slide, just to give you an idea of the format and expectations, we'll have 20-minute presentations. And I know a little change from our last mega meetup where we had 5 minutes for questions. Since we have two speakers this time, we're going to be giving them 10 minutes for questions. Feel free to add questions in the chat. We're hoping to have a little bit more, a little bit more questions and time to talk with the speakers since we have a fewer this time. And also thanks to the Cleveland Big Data Meetup, again to Doug Meal for just providing the advice on how to run our meetup and how to set formats. So appreciation to them. If you ever get a chance, you can check them out as well. All right, so the agenda tonight is we're going to have a quantum computing level set with John Marksick. So for all of you who are, brand new to quantum or just getting your feet wet, it'll be a quick 10-minute presentation. He'll go through some of the details just to make sure everyone's on the same page with some of the basics of what quantum computing does. Second, we'll be having Alex Condello from D-Wave presenting about quantum annealing and different use cases that they have. And from Zapata, we're excited to have Tamer, Elkholy, and Stephen N. Stern. They'll be giving a presentation about quantum algorithms, an Orquestra demo, and some use cases as well. And some announcements that we have. Upcoming, we're planning a mega meetup for early February 2022. Details to come later on that. Community, for those of you who haven't heard, Q2B is in its fifth installment in its largest quantum computing business conference. It's sponsored by QCware. They were a speaker at our last presentation. Joe and I both went to Q2B. It's an excellent conference, just has a lot of good content there. As you can see on the screen, there's going to be major presentations from a lot of the big companies, and D-Wave as well will be, I think you guys will be giving some important updates there and announcements. So we're excited for that. And I know Zapata has been there in the past. Are you guys going to be there this year as well?
Absolutely.
All right, fantastic.
Come visit us.
Yeah, so definitely, check out D-Wave and Zapata's, booths if you get a chance when you go there. And then just a note from Case, who we work with on these quantum meetup groups. They're planning to offer a course on quantum computing at Case Western next spring semester. So they'll have notes from previous attendance. All right, so again, announcements from D-Wave. If you're interested in learning more, you can contact Jonathan Garvin, and they will have some big announcements coming at Q2B, is my understanding. And some announcements from Zapata. So Zapata Computing was founded in 2017, headquartered in Boston, Massachusetts. They make ready-made applications for enterprise deployment. And just some of the more recent press releases. So their scientists are using quantum computing to help discover signs of life on other planets. It looks like you guys have worked with scientists from the University of Hull in the UK using their Orquestra platform, which we'll get to see today, a demo of that. You guys have presented at the White House and have a lot of different research that you guys have brought into play. So, excited to see what you guys have to offer tonight. All right. And now for our quantum computing level set, I'll hand it over to John, Quantum 101 in just 10 minutes. All right, John, you ready?
Yes.
All right. Awesome.
Why quantum? What do we expect to be able to solve with quantum computings? Historically, the first algorithm that generated a whole lot of interest in quantum computing is called Shor's algorithm. What does Shor's algorithm do? Shor's algorithm, you can input a very large integer. Think about an integer with, say, 10,000 digits, and you want to factor that integer into prime factors. Uh, Using a classical computer, it's very difficult. So it's a hard problem from a computational standpoint. And Shor's algorithm showed that a quantum computer is expected to be able to solve this type of problem sort of exponentially faster than a regular computer. Um, in fact, think of exponential as just extreme advantage. Why do we care about that? All of most people's encryptions on the internet are based on that. The problem of factoring integers is hard. So um, your social security number or your credit card number is safe on the internet because it's hard to factor numbers. So encryption is a big application there. Um, Another application where quantum is expected to give a great advantage is chemistry. Chemistry is, of course, the study fundamentally of molecules, and molecules are quantum mechanical objects. Also, this is another problem where classical computers have a hard time. There's just so many calculations to do that we can only basically model on a classical computer very small molecules. If you're doing pharmaceuticals or something with organic molecules that are really big, or proteins or something that has lots of electrons running around, uh, it's not tractable using a classical computer, but is expected to be using a quantum computer. The third type of algorithm gives you a quadratic pickup. It's not quite exponential like we have with the Shor's algorithm, but it's more generic. Shor's algorithm is very specific to a very specific problem. To apply that kind of concept to other problems, you have to do a lot of work. You don't get anything for free. But what you sort of get almost for free, or at least generically, um, for certain types of problems like optimization problems, whether it be in machine learnings, operations research, or even if you're trying to use Monte Carlo methods. If you don't know what a Monte Carlo method is, if you have a problem that's modeled as a probability distribution and you want to calculate, say, the average or the 90th percentile or some other statistic, what you can do is have the computer generate random numbers, and you can pull samples from it and calculate that statistic using those samples. So all of these problems sort of generically, and it sort of goes back to historically this Grover's algorithm, gives you a quadratic pickup. What's a quadratic pickup? If you think of a sampling problem for Monte Carlo, generally if you want to improve your accuracy by 50%, you have to double the number of samples that you take. Using quantum computers, it's hoped that you can calculate a similar accuracy with, instead of doubling it, multiplying by the square root of 2, which is, what is the square root of 2? I forget, but it's smaller than 2, so it does give you some pickup. What is the idea of a quantum computer? The idea of a quantum computer starts with a qubit. A qubit is simply a system, a quantum mechanical system, that when you measure the system, you will either measure it in one of two different states. We usually label those states as 0 and 1. If I have this state, I can measure it. It might be a 0, it might be a 1. If it's in the 0 state, we can output a 0 to a classical computer. If it's in the 1 state, we can output a 1. So this is sort of the only thing you can observe about a quantum qubit is what you can measure it in either a 0 or a 1 state. The states itself, you'll see on this slide, has interesting notation. You'll have on the left, you'll have a straight bar, and on the right, you'll have like a bracket. And that's to indicate that that's a quantum state. It's not technically a number. However, if you measure that system to be in that state, you can output a classical bit to a classical computer. The interesting thing that qubit can do is it can go into a superposition between the 0 state and the 1 state. What that basically means is that there's some probabilities, there's some weighting that it's in a 0 state, and there's some other weighting that it's in a 1 state. This weighting is the probability that you'll measure it in a 0 state or 1 state. And so it can be in a superposition between the two states. When it is in a superposition, when it's in a non-zero superposition, there's also an implied angle, or you can think of it as like an arrow between the two states. And later we'll be talking about when you're doing algorithms, you add states together, and if these arrows line up, you get constructive interference, so you amplify the signal. And if they are opposite of each other, say 180 degrees or close to that, this angle, then it destructively interferes so that you de-emphasize those signals. And the really important thing about a quantum computer is that you can have multiple qubits. So first, let's consider 2 qubits. So if you had 2 qubits, you can see on the slide, you could measure the first qubit in a 0 and the second state in a 0. So that would be our second qubit in a state 0. And so that would be the state 0, 0. So you can see you have that same funny symbols with the bar and the bracket. 0, 0 would mean it's in a state where if you measured it, you would get a 0 for the first qubit, 0 for the second qubit. But of course, there's 3 other states. You could get a 0 and a 1 and a 0, or a 1 and a 1. If you think about all the weightings, all the probability weightings, and all the angles that you could have between these states, what's interesting is that there's more parameters in a 2-qubit system. There's more than double in a 1-qubit system. So you can go to the next slide. So as you add qubits to your system, you somehow are creating more and more and more places to put information. More than double if you put 2, more than 3 if you put 3 qubits together. This extra information is generally referred to as entanglement, or sometimes maybe people refer to complexity of the quantum state. And the way it shows up is in the statistics is when you now measure the qubits, there's sort of the correlations between the first qubit and the second qubit when you measure them. So you can get a 0, 0 at some probability, a 1, 1 with some probability. If those probabilities are high, those would be positively correlated variables. So think about this as sort of a correlation between the different qubit measurements, but again, you can have n qubits, so go to the next slide. And if you think about all the parameters, all the different weightings between all the different states that you could have in an n qubit system, it grows very, very fast, as we can see on this slide. So you had 3 qubits, basically it's equivalent to having 8, so 2 to the 3, which is 8. 2 to the 10 is 1,000. 2 to the 20 is 1,000,000. So already when you get to like 300 qubits, you can see that number, 2 times 10 raised to the 90th power. You know, if you think about the number of atoms on the Earth or something like that, you'll quickly realize there will never be a classical computer that has a computational space that big. Go ahead to the next slide. So why don't we have quantum computers? It's been 26 or 7 years since Shor created his algorithm. What is difficult? First is that we cannot apply any operation to these n qubit states. We can only operate on 1 or 2, maybe 3 qubits at a time. So you have to do these little operations to try to create an algorithm that does something interesting. Generally, that's called complexity. Another one is it's a probabilistic theory. If you have 2 to the n possible outcomes of an experiment, and each of them have a tiny little weighting, you can imagine how many times you might have to sample depending on what you want to know. So that's a probabilistic problem. This probabilistic problem gives way to an algorithmic problem. What you want to do is find an algorithm that can use this constructive interference we were talking about with the angles between the states in the superposition to cancel out the answers you don't want or the things you don't want. And the states that represent the answer to the problem you're looking for, you want to amplify those. Unfortunately, just from a mathematical point of view, that's very difficult to do. And Shor's algorithm is like the quintessential algorithm that works sort of perfectly. And it's hard to find these types of algorithms. Stability. So this is about the hardware. Quantum mechanical systems tend to have lots of errors in them because they interact with their environment. So you have to isolate them from interacting with any other part of this universe, and sometimes with each other in a way that you don't want to. So the need for having an error correcting code also puts a higher requirement on the hardware. And the last thing is that these qubit systems tend to be hard to scale. You need tiny little controls, and well, it's a new in the past 30 years technology that it's hard to scale the hardware.
All right, thank you, John.
Okay, Austin, there you go.
Yep. All right, so like I said, that's a quick 101 on just all the different things that are facing the field, but also why we're excited about quantum. I'm going to move over to D-Wave, Alex Condello. Alex, are you ready?
I am, yeah.
Awesome. Okay.
Did I just steal the screen share there from you?
Yeah, and just have a little
Oh,
bio
sure.
for you. So just to give some background on Alex. So Alex is the director of algorithms at D-Wave. Performance and tools. He is one of the creators of Ocean Software, D-Wave's suite of quantum tools. Condello attended Queen's University, Canada, where he earned a Bachelor's of Applied Science in Mathematics and Engineering, Computing Communication, as well as Masters of Applied Science in Mathematics. So we're really glad to have you here, Alex. You can go ahead and take over the share.
Great. All right. We're going to be doing a little bit of juggling between two screens. This will be fun.
While you're setting up, I'll just make a note that if you have any questions for Alex, go ahead and either put them in the chat or save them to the end. We'll have 10 minutes for questions afterwards. And Alex, if you head over a little bit on time, we can use up some of that as well.
Sure, no worries.
Feel free to put your questions in the chat. All right, thanks. Go ahead, Alex.
All right, glad to be here, folks. So I'm going to be giving you another sort of intro crash course, this time to the type of quantum computing that we do here at D-Wave. And so at D-Wave, we really pride ourselves in doing sort of practical quantum computing. So, we've made a couple sort of hardware and model choices that have lended themselves to being useful to applications today. And I'm going to be talking a little bit about that. I also want to say before I get too far into it that in some sense, this is a pointless talk to listen to because most of what I'm going to be talking about is information that's available online and in open source. And I would really encourage folks to go check out our website and our GitHub and sign into Leap, where you can get access to a quantum computer for free. Just by signing into Leap, you get a free minute every month, which doesn't sound like a lot, but it's many thousands of jobs submitted to the quantum computer. And it's also, I want to mention that folks like you, and part of the reason I'm here talking to you, is that we really, really value feedback from folks like y'all, technical folks who are interested in quantum computing and are interested in getting started and using it for their applications. Because your feedback helps us prioritize, either whether it's good feedback, like I really liked this, or bad feedback, like I found this bug, or I found this confusing, or I didn't know how to get from here to there. All of that stuff is really, really important, and I can assure you that we take all of it incredibly seriously. And so I would really encourage you to get involved and sort of post questions and all that fun stuff. Okay, so let's talk about what it is you need to have in hand in order to do practical quantum computing. Well, the first thing you're going to need is a quantum computer. Seems kind of obvious. D-Wave has an annealing-based quantum processing unit. We have a 5,000 qubit processor that has over 35,000 couplers and degree 15 connectivity. So the last speaker sort of talked very briefly about how you can use qubits and how those qubits have to interact, and you can encode different problems into those qubits. When I say degree 15 connectivity, what I mean by that is that each of our qubits talks to 15 other qubits on average. Some of them on the edge talk to fewer. I also mentioned that this is an annealing-based processing unit, so a quantum processing unit. So it's worth mentioning that there are many, many different ways of implementing quantum computers. You can do annealing systems, topological systems, you can do circuit model systems, photonics, and there's different hardware implementations. There's, well, photonics, there's lots and lots of different implementations and ways to do quantum computing. And the particular variety that we've done is quantum annealing on superconducting circuits. So if you were to open up that box that I showed you on the last slide and you were to take a peek inside, this is what you would get what you would see. So our quantum computer, the actual physical quantum computer, is kept at about 15 millikelvin, which is incredibly, incredibly cold, 2 degrees colder than interstellar space. And really that whole box that's on the left-hand side, which is about the size of I don't know, a pretty big bathroom, is there to keep that quantum computer itself as much in isolation as is possible so that it can do the type of computation that it needs to do. So yeah, if I open up the box, what I would see immediately is what we call the chandelier. That's this sort of middle picture. The chandelier is a sequence of nested refrigerators, essentially. Think of like nesting dolls, that are each designed to keep the one inside of it at a colder and colder rate. So, at the top level, we're about 50 Kelvin, so, negative 20 degrees. Very quickly, you start walking down. It gets to 4 Kelvin, 1 Kelvin, 100 millikelvin, and then all the way down to 15 millikelvin. This is all so that we can keep our quantum processing unit in superposition and isolated from magnetic fields and radiation and photons and all the things that might hurt the computation. So this chandelier is, as I said, the overall box is about the size of a big bathroom. The chandelier is, I don't know, about the size of me. And then at the very bottom, hanging on the right-hand side picture there, is the sample holder. So that's about the size of, maybe my hand. And that's really where the quantum computer lives. That's where the control circuitry that talks to the quantum computer connects to it, and really that's the seat of the quantum computer itself. So if we were to pop that sample holder and we were to take a look at it, and we were to take off that little gold cover that it had on it, this is what you would see. And so this is that same sample holder, this time, again, about the size of your palm, this time kind of facing the screen. And in the very middle of it, you can see the quantum computer itself, which is about the size of a thumbnail. That's where our actual quantum computer is. That's where the qubits are, the 5,000 qubit system. And that's really where sort of the magic happens. And everything else, all of that other infrastructure is to keep that safe and isolated. One question that I get asked fairly regularly, which I might go ahead and answer now, is, well, could you make it smaller? And the answer is yes. I've been told that we could probably get it down to the size of a small refrigerator if we really wanted to. But it's also important that we be able to, take it apart, reassemble it, disassemble it, change things, make upgrades, all that fun stuff, so that we can keep doing the latest and greatest technological development on our systems at all times. So now we're going to leave the realm of actual pictures, and we're going to start talking about, we're going to move into a little bit more of an abstract representation or mathematical representation. So if we kept zooming in on that processor and we started looking at the individual qubit bodies, we would see that they are laid out in the way that's sort of defined by this picture. So what I want you to imagine is that each of these white bars is a qubit. And it's in fact not actually a bar, it's a loop of metal. So a little stretched out loop of metal. And where those bars butt up against each other end to end, and where those bars cross each other, that's where the qubits interact. So I mentioned before that each qubit in our processor in the center of the fabric here connects to 15 other qubits. And you can, if you sort of were to count all of the qubits that cross it and all of the qubits that bump up against it, you would arrive at 15. That's the number of qubits that it talks to. And we've laid out our qubits in this way in order to maximize that connectivity, because the more connected that your qubits can be, the more powerful a computation that you can do. And so ultimately, this induces a representation or a connectivity graph over those qubits that I'll actually be showing a little bit later. Okay, so now we're going to go even more abstract, and we're going to talk about mathematics. And specifically, we're going to talk about the Ising or Ising Hamiltonian. So the details of this don't really matter. If you have a physics background or a math background and this is super clear to you, that's awesome. If they're not, then don't worry too much about it. This is just the equation that defines the behavior of our quantum computer at different parts of the anneal. And specifically, I want to draw your attention to a part of this on the right-hand side. This little mathematical expression, which is we call the quantum machine instruction, is the part of the quantum computer that, if I am a user of the quantum computer, I am typically engaging with. So when we say that we're going to program the quantum computer or use the quantum computer for computation, what we are saying is that we are going to be adjusting the h and j values in this equation. And those h and j values moderate the relationships between the qubits and moderate the values that the qubits take over the course of the anneal. In mathematical terms, for any of you who maybe have a background in optimization or industrial engineering, this quantum machine instruction actually is a so-called binary quadratic model, which is a particular class of optimization problem. It's an optimization problem that is over binary variables. And the reason that we use binary variables in this case, and actually the last speaker alluded to this, is that our qubits at the end of the anneal will either have their current going clockwise or anti-clockwise in them. And so you can represent this, this object that was in superposition, you can map it to a classical bit, 0 or 1, binary. Our qubits, this binary quadratic model also has quadratic interactions, which is to say that our binary variables interact with each other pairwise. And those are those couplers. So remember I mentioned that the qubits touch each other. That's a pairwise interaction. One qubit can affect the other. So we get a quadratic interaction. And then finally, our binary quadratic model, we have a linear objective over those qubits. So we can apply weights to the individual qubits. I can say to one qubit, I want you to end your calculation either in the 1 position or in the 0 position. I can bias them individually. And so we get this binary quadratic model optimization problem that can be encoded as a quantum machine instruction. And this is important because this binary quadratic model is in this NP-hard class that the previous speaker referred to, this complexity class that you can map different problems to relatively efficiently. You can map problems within that class efficiently. Okay, so that's the sort of, so just zooming in once more on this binary quadratic model, I said a bunch of words. Maybe, again, if you have a physics or math background, hopefully that was relatively clear. Even if not, I hope that was at least metaphorically clear. But the main takeaway is that it's a quadratic polynomial over binary variables defining a cost function. So for every possible string, for every possible configuration of binary variables, I can represent the cost using this binary quadratic model. It's also worth mentioning this is known by a lot of names. It's also known as a QUBO, a quadratic unconstrained binary optimization problem, or a PUBO, a polynomial unconstrained binary optimization problem. It's also known as an Ising problem. There's lots and lots of different representations for this problem class, which you maybe have run into in your wanderings of quantum computing. To make this then a little bit more sort of metaphorical, I'll mention that the way that we actually think about this BQM, even if you're like me, you have a math background and you do this every day, is that we often think about these in terms of defining an energy landscape. So you'll remember that I said that this thing has binary variables. What I mean by that is these binary variables can say define a location on this landscape. So you can imagine it's like GPS coordinates. It tells you where you are on your landscape. And the binary quadratic model itself defines the cost, the height at where you are on any point in that landscape. So for every possible configuration of binary variables, I know where my height is. And the goal, in some sense, is to find the lowest point on that landscape. The quantum computer, in some sense, is attempting to find the lowest point in an energy landscape defined by this binary quadratic model. And so the whole game is to represent your problem in such a way that the lowest point, the lowest energy, the lowest cost is the solution to your problem. Okay, so let's talk a little bit about an example to hopefully make this a little bit clearer, like what this looks like when we actually try to solve a problem, in the real world with this technology. So particularly, I'm going to be looking at a particular problem called structural imbalance. This is over something called a signed social network. And the way that I want you to think about it is imagine that I have a group of people in a room, say a quantum computing meetup. And these people have relationships amongst themselves. So sometimes they're friendly relationships, sometimes they're hostile relationships. So there's this sort of complexity to the network. And the goal of these structural imbalance problems in general is to divide up the people in your network in such a way that it minimizes frustration. And by frustration, what I mean is, let's say I'm putting us all into one team, so I'm not going to divide us up at all. I am frustrated to have people that I have a hostile relationship on the same team as me. Likewise, if we were dividing us all into 2 teams and one of my friends was on the other team, I might find that frustrating. So the goal is to divide up our agents in such a way that minimizes frustrations. It tries to keep friends on the same team, and it tries to put hostile relationships on separate teams. And so if we want to represent this problem as a binary quadratic model, there's actually a really native and obvious way to do this, which is that, remember, our binary quadratic model has binary variables. They're 2 states. So I want to divide my social network into 2 teams. I want to be on the 0 team or the 1 team, binary. There's quadratic relationships in my model, which is that the relationships are either friendly or hostile. So I want two friends on opposite teams to cost me $1. Remember, we're building a cost function. Or I want two enemies on the same team to cost me $1. And so again, the quantum computer will then try to find the cheapest solution, which is the one that minimizes the frustration and minimizes the number of rule variations. And so this structural imbalance problem can be mapped really natively to the quantum computer via this binary quadratic model. And this is, again, the actual binary quadratic model that encodes this problem. It doesn't really matter the details. So what I'm actually going to do now is I'm going to do something mildly brave, and I'm going to do a live demo to show you what this actually looks like in practice. Like, how do we go about mapping this problem to a quantum computer? And so I'm going to go ahead and swap screens real quick. And I'm going to go ahead and sign into Leap, which is our online cloud learning platform. This is our online quantum computing platform, rather. This is, if you were to sign up for Leap today, which you can for free, you would see this page. And this is where you get information about your access to the quantum computer. So I've actually just signed in with like my Gmail account. And here I can see, how much access to different systems I have. I can see some problems I've submitted. I can see what QPUs I have access to. So for instance, I have access to a couple quantum processing units, and I have a couple hybrid solvers available, all resources that I have available right now to submit problems. There's lots of other really cool stuff in here, which unfortunately I won't really have time to show, other than I'll mention we do have this community. We would encourage you to come check it out and make posts and ask questions. But what I'm actually going to do is I'm going to pop into a collection of our online examples. So these are different ways of using the quantum computer that we have compiled and implemented so that you can check out how it is we solve different problems. So you can color maps, you can schedule nurses, you can place satellites, all sorts of different things that you can use the quantum computer for. So specifically, though, I'm going to continue this structural imbalance theme, this signed social network theme, and I'm going to go ahead and load up the solution, the actual code, the real Python code that implements this signed social network problem in our online integrated developer environment available in Leap. So in Leap, if you are a programmer who wants to get access to the quantum computer and wants to submit problems, you can actually have everything pre-installed and ready to go in an environment, with a click of a button and a couple seconds. So this is a full-fledged development system. And I'm actually going to go ahead and I'm going to run this signed social network problem on a bit of a bigger one. I'm going to run it on our quantum processor unit, and I'm going to go ahead and use our inspector. So when structural imbalance inspect. Live demos are fun. What's happening right now is it's running the Python code that implements that problem that I've mentioned. And it's actually running live on a quantum computer, which to me is still pretty darn cool that, with a click of a button, I can run on a quantum computer. And it's going to be making use of our quantum computer available in Burnaby. And here we go. We've gotten a solution from the quantum computer. So if I take a look, this is the social network that I have in my social network. So you can see it's pretty complicated. There's a lot of different nodes. Some of them are more popular than others. This one talks to a lot of people. This one only has a few people. And then the relationships between those nodes are also defined. So these negative relationships, these are friendly relationships, and these blue lines, these are hostile relationships. And I can see different solutions that were returned by the quantum computer. I can see how they were assigned, whether to the red team or the white team or the blue team as I scroll over them. But the really cool thing that I can do is I can actually see how this problem was mapped directly to the quantum computer. And so on the right-hand side here, you can see a representation of one of our quantum computers. In this case, this is one of our 5,000 qubit systems. And you can see how the different members of this signed social network were mapped to the qubits on the system. So you remember that I said the reason we like this signed social network problem is that it maps directly to the quantum computer in some sense. This is a native representation. And you can really see that. Like I have this lonely node over here. And I can see exactly this is social, this is person 43 in our social network. And you can see that person 43 got mapped to qubit 4,823. And I can see that this qubit connects to one of its neighbors, this one here, which is mapped to a different node in the original problem, this one. And so I can really see how this problem gets mapped directly onto our quantum computer using the Ocean software. So with that, I think that's actually about 20 minutes. So maybe I'll cut it there and I will see if there are any questions folks want to ask. I think there were a couple things that showed up in the chat.
Hey, that was really fascinating to take a look at.
Great.
So one of the questions that we have in the chat is from Anna. What has been done in quantum chemistry with the D-Wave processor?
Sure. So we have a couple different things. I'll first off say that D-Wave mostly works on industrial optimization problems. So in the context of quantum chemistry, that tends to look like not doing full, say, simulations on the quantum computer, but rather doing problems that are sort of adjacent to it. So for instance, we've done de novo protein design on the quantum computer. We've done different sorts of trial development and different sort of pharmaceutical applications. But when it comes to doing sort of like quantum chemistry simulations, that does tend to be more of a circuit model system. Problem class, which is one of the reasons D-Wave has recently announced that we are also going to be building a circuit model system, although we're sticking with our annealing platform. So for right now, we tend to mostly focus on the optimization side. Should I just read the questions, or Austin, are you going to read them to me?
I can read them to you.
Sure.
Yeah, so another one we have from Sandeep. You talked about different implementations of quantum computer. Are the algorithms tied to the implementation, or are they implementation agnostic?
Yeah, that's an awesome question. So the short answer is that each quantum computer has a sort of native problem class that it wants to solve. And so ours is this binary quadratic model, this Ising problem. Circuit systems want to solve, circuits. And so in some sense, they're different. However, there are some very lovely theorems that will tell you that universal quantum computers of any variety are equivalent, which means to say that even though they solve different problem classes natively, you can map your problems between those classes relatively efficiently. And so in theory, any universal quantum computer rather, can solve any problem that any other universal quantum computer can solve. In practice, I will say there's many devils in those details, and so that's part of the reason, for instance, that we at D-Wave, mostly use our annealer for optimization problems, is because that's sort of the main problem that it likes to solve. And although we can sort of coerce it to solve other problems, it's not its native language, as it were.
Okay. I have another question out there. Is the topology between the qubits dynamic, or is it set before the computation begins?
Yeah, awesome question. It is static. So we actually print our qubits onto a physical piece of hardware. In practice, your problem can be arbitrarily structured. We have ways of using the static structure of the qubits to represent problems of arbitrary structures. It's called embedding, which probably is a little bit beyond the scope of this talk, but it's very cool stuff. You can check it out on our technology, on our website. And so, but the actual hardware is static. Each system has a fixed topology.
Hey, real quick, Joe, do you mind adding in D-Wave's website into the chat, just that way people can check that out? And then I'm going to actually form a question for you from one of the comments. So, one of the things that we heard at the beginning is, in the level set is, the power of even 300 qubits is, looks like more computational space than all the atoms in the universe. So since you guys have a 5,000, qubit annealing computer, why haven't we solved all our problems yet?
Yeah, no, it's a great question. So it's worth mentioning that there are, and actually probably the next talk will get into this as well, but there are many differences between a theoretical statement about the size of the problem space that can be solved with a 5,000 qubit system, which is 2 to the 5,000. It's an enormous problem space that if you were to explore completely, would take very, very, very long periods of time. However, we live in an era of new technology and noisy systems, and so it is the case that classical computers are still competitive for many, many different problem classes. And it's worth mentioning there are problem classes that classical computers will always be state of the art. Whereas there are also problem classes for which we can show performance benefit to using the quantum computer. There's a couple papers that I could share that they tend to be a bit in the weeds that sort of give examples of different problem classes that we can sort of prove that we're seeing performance benefits and scaling advantages for the quantum computer. In between are practical problems, and there it just tends to be kind of an apples to, you just run it, you A/B test it, like you try it on the quantum computer, you try it on the classical computer, and see which one works best. And a lot of what I do day in, day out at D-Wave is run that experiment for different problem classes and for different customers, and sometimes we win some and sometimes we lose some.
Okay. I think a related question from John is, if there is noise in the system, how sensitive is the solution to this noise? How stable are the solutions?
Yeah, okay, that's an interesting question. So the technical answer is that our quantum annealer is a finite temperature sampler, which is to say that it is noisy, it has some randomness to it, and it has a temperature, and by temperature, it's sort of a measure of how random it is. In practice, we do sample from the same distribution. So in sample to sample, there's a little bit of an asterisk. There's some long-range effects, but in general, we sample from the same distribution, and so that is stable. Your particular problem, depending on how degenerate it is, and by degenerate, I mean like how many different solutions it has, you might get different solutions for each run of the quantum computer if it's a really degenerate space. So it might be sampling, say, uniformly from those different degenerate solution space. So this is a long way of saying that it is consistently random. So it samples from the same distribution, and depending on your particular problem class, you can sample from good solutions that are very high probability, but it is noisy and there is some randomness in the system. And before I mentioned like, oh, you get a minute of free time and you can use that to submit many problems. In practice, when I'm solving problems on the quantum computer, I'm not generally just running one anneal, which takes about 5 microseconds. I run many anneals, hundreds or even thousands of different runs of the quantum computer, and I just take the best solution that it found over all of those different runs.
Also, add a note out to the audience. You don't have to type your questions, in the chat during these questions sections. If you have something that you want to ask or anything that you have, a question about, feel free to, go off mute and yeah, let us know what your questions are. Oh, I've got one in here. I'm going to take a quick moment. Does anybody else have one that they wanted to just ask out loud? If not, I've got a couple more in the chat that I'm going to do. I think I'll do these two in the chat, and then we'll open up for, I think, one last question. It should be a good time. Okay. So one of our other questions says, thank you very much, Alexander, for your time. My question is, to find the solution that you have demonstrated, how do you optimize the quantum circuit? Is there any quantum circuit involved here? I am new to D-Wave, QC, and other quantum computers. The concept of quantum circuit is more prevalent.
Totally, yeah. There isn't really a notion of a quantum circuit in the context of quantum annealing. There's some asterisks there again that you could make some arguments about, but in general, we are working with this binary quadratic model formalism, which is actually the same optimization problem that you can use to solve like QAOA style algorithms, although there's recent work showing that gate model systems are sort of ill-suited for that problem class in some ways. So we don't really do the same thing as the quantum circuit, although there are analogous ideas to having been given a binary quadratic model. You need to do some manipulation to fit it onto the quantum computer, and there's different sorts of optimizations or pre-processing you can do with a classical computer that's relatively inexpensive, but has sort of a big benefit to the quantum computer later. And one thing I unfortunately didn't get to spend much time on in this talk is hybrid computing. That's what I actually do for a living. So hybrid computing is combining both quantum and classical algorithms together to get the best of both worlds. And that's really what that's about, is taking sort of arbitrary problem classes and doing manipulations to those problem classes so that you can get the benefit of a quantum computer and classical computers for solving your problem.
All right, it's 6:48. I think we got about 2 more minutes roughly. I'm going to go ahead and ask this last question. If anyone has any more questions, feel free to keep putting them in the chat. And Alex, I know you're going to have to leave early.
Yeah, I can stick around for a couple minutes and answer
Yeah, and I
questions
don't
in the
know
chat.
if Jonathan's still here, but go ahead and post your questions. We'll end up, we'll pass them on to you guys. Is that okay?
Mhm.
Okay. All right. So from Hart, can you provide some information on your work in chemistry? Any work done in molecular modeling?
Sure, yeah. I'll go ahead and just drop some links in the chat for that, and rather than answer out loud, because it's better to get the actual information from the use cases themselves. So I'll drop some links in the chat.
Okay. Well, awesome. Really appreciate the presentation, Alex. Yeah, that's some really fascinating stuff. And I know it's interesting to see, especially what you guys do at D-Wave, since you guys are kind of known for the quantum annealing, which is different than a lot of the other computer, I guess, formats out there. How they work that. So, all right, Alex is posting some comments in the chat. If you guys are interested, definitely check that out. On this, I think we'll transition over to Zapata. And I'm going to go ahead and share screen again. Tamer and Steven, are you guys ready?
Yep. Sure.
All right. I'll go ahead and do a quick introduction. All right. So Tamer and Steven are going to present quantum algorithms, talk a little bit about Orquestra and some of their use cases. So Tamer is a quantum solutions engineer. Tamer is a physicist with a background in both industry and academia. He studied galaxy clusters and cosmology for his doctoral thesis at MIT before joining Hewlett Packard in a consulting role in enterprise software. He then returned to physics, taking an assistant professor position at the Zewail City for Science and Technology in Egypt. He has turned his focus now to quantum computing, where he aims to combine his physics, computing, and consulting skills. And then Stephen is a director of quantum solutions at Zapata. Stephen is an experienced enterprise program manager, having led Fortune 100 in public sector operations, engineering, construction, service delivery, and sales teams. His expertise includes gathering requirements, site planning, architecture design, technology selection, and project management to plan, build, and deploy large-scale client infrastructure. Steve received his bachelor's degree in electrical engineering from State University of New York at Binghamton and his master's in business administration from Adelphi University in Garden City, New York. We're really glad to have both of you guys. Awesome stuff. We're really excited to see what you have to present. With
Likewise.
that, if one of you wants to share screen, if you guys have
Tamer's going to drive and run this presentation for us. So, and I'll answer the chat, or we can just field the questions after, whatever anybody wants to do.
Okay. Awesome. All right.
Let me just give me a second here. Okay. Not able to share. Let me try again.
Okay.
Okay. Can you guys see my screen?
Yep.
Perfect. Great.
All right. Awesome.
So we're super excited to be here. Thanks for inviting us to speak. My name is Tamer, and thanks for the introduction. I think you gave an introduction. Let's dive right in. This talk is going to be slightly more different. I really enjoyed the previous talk with the deep dive into the technology. For this talk, will be a little bit more high level, where we're going to talk more about a little bit about our company, and then we'll talk about our software platform, Orquestra. We'll talk about some use cases. And I think we were going to stop there. I think I forgot to remove this part here. We don't have enough time for that one. Sorry about that. So a little bit about Zapata. So Zapata is one of the leading companies in kind of getting the quantum algorithms and quantum methods into the hand of top companies, enterprise, at the enterprise level. So we started back in 2017. We were spun out of Harvard from the group of Alan Aspuruguzik, who is a leading quantum computing scientist. So our goal was and is to build, quantum computing solutions for optimization, machine learning, chemistry simulation, specifically for enterprise problems. And the way we do that is through Orquestra, our platform, which I will discuss briefly today, and a lot of service engagement, consulting engagement with customers, where we kind of share our expertise and know-how through our quantum scientists. We've had a lot of customer impact from in very big companies, in energy and foods and beverages, and in chemistry, and also in finance. These are some of the customers we've worked with. I also just want to make a quick correction, just to kind of like set the expectations right. So we aren't planning on doing any demo today. The demo is for Q to B, so you guys should be there, try to attend and watch the demo there. It's going to be exciting. So this is briefly our team. This is Alan Aspuruguzik, who is our CSO. Out of his group came Yudong, Peter, and all of these guys with the green names here. These are our founders. They bring a lot of quantum computing expertise. And from the business side, we were led by Christopher Zewail, who has also a lot of experience driving, startups and businesses. So we combine a lot of both words, the business know-how and the science know-how, and also the engineering know-how, as you see in this next discussion. This is kind of like a big picture view of what we really stand for and how we're building our company. The main pillars that are going to sustain this company going forward. We think it's going to be about platform, building a strong platform that kind of helps answer these business needs, building a lot of, and also using a lot of our expertise to do these service engagements where we kind of directly share our knowledge with customers. And finally, we're building a very strong portfolio of IP. All of our inventions are used to build this company. And I feel like we're very well ranked in terms of, if you look at just the quantum computing companies, we're very competitively ranked. If you just look at the number of patents that were filed. So, oops, sorry about that. So our mission is to deliver first mover quantum advantage for the enterprise. So how do we do that? And the way we do that is, first we want to leverage our scientific know-how, all the insights, all our expertise. We have a good concentration of quantum scientists in this company. If you just look at the worldwide, population of quantum scientists. And then we also want to look at what's technically feasible, and we want to build, all the capability for us to scale to enterprise problem, and also look at which problems are technically feasible today and which ones are technically feasible tomorrow. And then finally, we want to look at the problems that have business impact. So a lot of conversation with customers to understand their problems, filter out which ones are, tractable with quantum computer, suitable for quantum computers, and dive deep into the intersection of those three. And the way we do that is with Orquestra. So Orquestra actually came to life because of our own needs when we were working with customer problems. So we needed a tool that can help us run these hybrid quantum classical algorithms repeatedly with variations in each run, and also at scale. So, and on top of that, we wanted a solution that will keep track of all the data that's moving between the different pieces of the algorithms, and keep track of the outputs as they are as they come out of different variations of these runs. So it's a tool built for the either for people in either enterprise or academia who are trying to explore what quantum can do to them today, and kind of extrapolate to what it can do when the hardware becomes even more powerful and can actually deliver on these promises that were discussed, in this in the first part of this talk by John. How does Orquestra work? Very briefly, it's just 3 stages where we first compose our algorithms with many quantum libraries that we have, and also other libraries such as machine learning or chemistry libraries. They are integrated. We then, in the second stage, after the user creates their algorithm or their workflow of steps, these are run. The orchestra will orchestrate these steps together, and will run them on classical and quantum hardware in the most efficient way, parallelizing when possible, serializing when necessary, and to make this run in the most efficient way, and in a very scalable, and using a very scalable methods in just the classical in the classical software engineering part of the problem. And then finally, the last part is where we evaluate the results of our runs, and we want to be able to be able to display it in different ways, and also keep track of all the metadata that was used in the previous steps to give the results that we see. So again, this is a tool where we want to, you want to think of someone sitting in an enterprise that is evaluating how well a quantum computer will solve my problem. And so there's a lot of scaling the problem to bigger sizes, tweaking the different parameters of the problem to find what the best solution is. And so at the end, you want to be able to track back all of these variations and be able to tell which ones worked, which one didn't, and go forward from there. So let's talk a little bit about use cases that we encounter today. This is just a very, it's a long list of use cases, and I'm just picking here a couple of fields. Like in biopharma, there's optimization, machine learning, and simulation and modeling. These are all the different chemistry problems that you can track. And you can see here in green, these are the different use cases where we can apply some of our Zapata IP. So in another kind of realm in chemistry and materials, there's a lot of other simulation and optimization problems that we can tackle with our IP and with others that can be integrated in Orquestra and that we know how to deal with with our expertise. I will focus now on just 2 of these use cases, and one of them is related to a customer, VP, who was an energy company that we worked with extensively, and one of our first projects with them was to kind of use it to kind of like do a resource estimation for their problem. So in the context is, we know very well that quantum computers are built to solve chemistry problems because chemistry is based on quantum mechanics. Quantum computers are based on quantum mechanics. So there's a very good mapping between the 2. So, but the question is, when will quantum computers be able to deliver the advantage that we expect from them? And so that was something that was very important for a company like BP to find out. That's how. So we used our hybrid quantum classical algorithms, coupled with a lot of innovations to kind of tackle this problem. we use Orquestra to do all of these experiments where we kind of take these molecules and look at a specific problem. In this case, it's the combustion problem, and you can look at this reference here at this paper for the details. So how can you then map your chemistry problem to existing quantum computers, and what kind of quantum computer will be able to give you the advantage over a classical computer in calculating the combustion energy of these molecules. We did just that. We made an estimate of the size of quantum computers needed for that, and you can see the result in that paper. And that was just the first stage of that engagement, and the one that was made public so far. And so hopefully, as other results are being made public, we can talk more about them, and you can keep track on our website to find out more about the future results from this collaboration with BP or engagement with BP. The other area which we're really super excited about and we've done a lot of work on is on machine learning and optimization. So I want to talk here about quantum enhanced optimization, and it's a very different way of doing optimization. So we've seen we've seen that the QUBO paradigm that Alexander talked about from DWA, and and we worked with that too. But there's this one, this approach to optimization is very different. In this case here, we're using actually machine learning to do optimization. I'll tell you just how. So it's based on quantum enhanced generative modeling. And let me tell you about what generative modeling is. So generative modeling is a machine learning approach where you learn the probability distribution underlying a data set, and you try to use that probability distribution, you model it, and you generate new data from that distribution. So, for example, one of the ways that these generative models were used is using these generative adversarial networks, GANs, to create new images, new faces, new images of people's faces, right? So all of these people here on this website called thispersondoesnotexist.com, all of these images are of people that do not exist. How were they generated? Well, these GANs were able to understand what an image of a picture of a face looks like. And so, there's a lot of variation of how faces look like. And so by learning all this very wide distribution of what a face looks like on an image, these GANs are able to generate these pictures. So this is not quantum, this is classical in this case, in the case of this website, but what we're trying to do here is see if we can apply quantum computers to this kind of problem. So, and so this is something that we believe is promising for quantum machine learning. So how does this apply to optimization? So we're going to do the same thing now. We're going to use the machine learning to understand what good solutions to an optimization problem look like. In a slightly more technical language, that means we're going to learn the distribution of low-cost solutions to an optimization problem. And then once you do that, we're going to generate similar solution in the same way that, again, generates images of people's faces. And when you do that, well, in a slightly more technical language, we're going to use generative modeling techniques to sample from that model and produce more good solutions or more solutions. And then let's see whether they are good or bad. And then once you do that, then you have a new data set of your original data set of solutions to the optimization problem, plus your generated data set. You can merge them together and find out which out of that union of those two data sets, which subset is the one with the better cost function, right? And so when you do that, now you have the new data set, and then you can repeat that same process again and keep improving your solutions until kind of you reach kind of like a stable data set, right? So we did apply this method, and we applied it, and we haven't talked about quantum yet. All of this, you can do this in classical, and what you'll see is that when we do this with quantum as well, it kind of enhances it even better. So we applied this problem to portfolio optimization, and in this paper here, this is the reference if you'd like to track it down. So the blue distribution here, so what we're doing here is that we're finding, we are setting a certain level of return, a percent return value. So let's say you want, I don't know, a 10% return. And then we're looking at all the different portfolios that give you this level of return with the minimum amount of risk. So each kind of like point on these two histograms is a portfolio. So a portfolio means like just, a set of stocks that you're gonna invest in, and then with an expected risk and an expected return that matches your fixed return. So let's say you pick a return, and then you ask what is the portfolios with lowest risks for that given return. And so you can do that, with normal classical optimization techniques, and you get this blue distribution here. And so that's going to be our seed data that we're going to plug into our QEO algorithm. When you do that, you get a new distribution of portfolios, so a new set of portfolios, and you can calculate the risks of these portfolio. And what you find is a distribution where you can, our GANs kind of imitated, our generative models imitated that structure inside of the portfolios and produced portfolios with lower risks, as well as those with higher risk. But we don't care about those. We only care that we found a better solution here. So that's how QEO worked. We implemented this not on a quantum computer, but using these MPS kind of simulation techniques that are quantum inspired. So these are classical implementation of quantum inspired algorithms. But if you had like a quantum computer with a large enough number of qubits, you can do just that. So then your next question would be, so how did you see a quantum advantage in such a problem? And the answer is, we didn't see it in this exact problem, but we saw it in another generative modeling problem. And in this case here, we were trying to generate handwritten digits. I'm not going to go over this, but we implemented, I'm not going to go over this in details, but we implemented this problem. And this problem, very quickly is, can you learn the distribution of a large number of handwritten digits, and from a data set called the MNIST data set? That's a very well-known data set for all machine learning enthusiasts. So that problem consists of just a large number of handwritten digits, images of those handwritten digits. And so the question is, can you use that data set to generate new handwritten digits? So it's similar to the faces, generating faces, but a little bit more low resolution. And in this case here, what we can do is that, yes, we can actually implement it on a quantum device, and we did implement it on IonQ's 8-qubit device. Sorry, I think it had more qubit, but we just used 8 qubits from that device. And in that case, we were able to map the problem down to 8 qubits, which is not the case, for example, for the portfolio optimization problem, because we're looking at 500 stocks, so that doesn't really fit into an 8 or 10 qubit quantum computer. But in this case, there are ways to kind of map each image down to 8 qubits. And in this case here, we're able to generate new digits. And if you look at the inception score, which is kind of a measure of both of the quality of those digits that come out of your generative model and their diversity as well, because you don't want to have a model that gives you the same 4 written in the exact same way, drawn in the exact same way every time. So there's a measure called the inception score, which measures both of those aspects, quality and diversity. And you can see here that as you train the model more and more, it starts to kind of get better than the classical models here. And that's the orange point here, the ones coming from the IonQ device. And the blue points are coming from a simulation of a quantum device as well. But the classical result is those black squares here. So if you zoom in here, you start to see a slight quantum advantage. And what we believe will happen is that as your problem gets bigger and bigger, and you have more qubits able to do this kind of computation, you're going to start to see an increase in that, more divergence between the quantum and the classical results. So I think that's all I had to say for today, and I'm happy to take questions.
All right, thank you very much, Tamer. All right, let me check the chat. Looks like we got a question to start off with. So thanks a lot, Tamer. So you guys are using all sorts of quantum hardware, trapped ion, superconducting qubit, etc., for your algorithm design, or are you primarily leaning towards any specific quantum hardware for the algorithm? And he says you have already shown solution through trapped ion from IonQ.
Yeah, so I think I forgot to go over this. Yes, so we do have integration with many of our of the quantum hardware manufacturers. So we can work with Rigetti, IonQ, Honeywell, IBM. I think what in the big picture is we don't want to be just working with one quantum hardware, because we don't know which of these is going to be the winner in the long run. We want to be able to kind of like work with all of them, so that our customers, the ones who are really actually trying to solve a problem, when they come to us, we can solve their problems using the most suitable quantum hardware today and in the future as well.
I think, Tamer, I think I've heard you guys explain it before, and correct me if I'm wrong, but you guys serve more as that, I guess, broker in the middle who kind of helps an enterprise choose which technology is going to suit them best. Because I know people, I think, have heard more of some of the companies out there who have a quantum computer. You guys are helping people choose the right one. Is that a good description?
Well, that's one of the things we do. Yeah, of course. So we're here to solve enterprise problems, and the idea is to do it with the best tool. So if today someone comes to us and we can solve their problem, even with just classical, we'll do it. But of course, we're a quantum company, and so we're looking at quantum algorithms to solve quantum problems today and in the future. So yeah. So, but of course, to add to just make to add to what you just said, we're here also to build those solutions. So we do provide all the expertise to kind of find solution to these problems, which sometimes we have them in our own IP, and sometimes we develop them in a given engagement. So I think that's where a lot of the value comes to customers from, when they work with us.
Okay, so more of like a one-stop shop that can help, current problems today, and then help bridge into, solving those problems with quantum solutions as time goes on, or with classical. Either way, depending on what best suits the customer. Okay. I got another question in the chat from Jason. Does quantum computing in terms of machine learning provide for better model interpretability for more complex algorithms?
Ooh, that's probably a more technical question than I have, but it's not, what we've seen in this handwritten digit experiment is that one of the aspects that came out of it is that, and then that's kind of like the question that I had for our scientists too. So why quantum for machine learning? What's better? What's the advantage that comes with it? And what they're seeing today is that there is more expressibility. So these quantum models are able to model these distributions better, perhaps because of these extra correlations that exist between these different qubits that cannot be mimicked classically. So that's one aspect that comes from quantum machine learning, and our teams are working to kind of like discover what exactly is making these methods better than the classical ones.
Awesome. All right. Do we have any more questions? I'm not seeing anything in the chat, but a lot of good stuff here. And you guys said that you'll be doing a providing information and demonstration of the orchestra at Q2B.
That's correct.
Yeah.
Okay, that'll be very exciting to see.
Yeah. I'm just gonna say that it looks good.
Yeah, it's always exciting, and I do think that's also, I think for some companies out there, they're looking, they see a lot of different, IBM's got a computer, Google's got a computer, Rigetti, Honeywell, IonQ, there's many others out there, and I think you guys provide an interesting solution to well, which one do I choose? How do I interact with that?
Mm-hmm.
And also I think to what you pulled out earlier, the fact that you guys handle the classical as well, that can also help companies bridge the gap between, I got a problem today and I'm solving it classically. I don't know how to upscale that problem to something beyond what the classical can handle, or it's hard to convince business that we're ready to give quantum a try. So it seems like you guys are helping bridge that as well.
Yeah, absolutely. So that's one of the main advantages of Orquestra, is that we do all the hard work of the classical solution, the classical software engineering. So all the scalability aspects that are needed in some of these hybrid quantum classical algorithms. So today a lot of our quantum computing problems are approached with this hybrid classical quantum approach, where what you have is a lot of back and forth between a classical computer that does some part of the problem, and then quantum quantum unit that does another part of the problem. And so when you do that, you do want to have kind of there's a lot of classical infrastructure, classical computing infrastructure that you need to build, and it needs to be scalable depending on your problem. And even if you are not using a quantum machine per se, you may want to simulate a quantum machine, and that's where actually a quantum a simulator might require a lot of classical computing resources. And so we do a lot of simulations, for example, to benchmark how many qubits do we need for this problem, or what kind of qubits, what kind of errors do we need to solve this problem. And when you do that, your computing footprint starts to increase, and you need to be able to manage that. and that's what's baked into Orquestra.
Awesome. Last call for any questions. Just give it a second here. Well, if not, really excited, glad that you guys came out. A lot of good information, and we're excited to see what you guys have to present at Q2B.
Thank you for
Yeah,
hosting us.
thank you,
Yeah.
Austin. Thank you, Joe.
If someone's interested in learning more from you guys, is there a good contact point?
Yeah, you know what? We'll Tamer and I can both provide our contact information, and we could put it in the chat here, or we could send it to you, Austin, and you could share it with the group.
Okay, that works. How about you guys put in the chat, and
Yeah.
that way it'll be available to everyone. All right. Awesome. Well, with that, we're gonna close up here, but just wanted to let everyone know that we are looking to have another mega meetup in probably either late January, early February. Still working on details for that. So we'll be sending out more information as we secure speakers, and also, yeah, as always, a plug to Q2B and the Cleveland Big Data Meetup group. A lot of good places to get information and see great presentations out there. So thank you so much again to our speakers today. Tamer, Stephen, and I know Alex had to leave a little bit early, but just that, yeah, thank you so much for spending your time and showing us what the future might look like.
Thank you all for
Hey,
coming.
thank you.
All right.
Hey, Austin, can you hear me?
Oh, yep.
Hey, sorry, my name is Pathikrit Mukherjee. So, a question for you, since are you guys are from Cleveland, right? Not all of you, I can understand that, but is there any meetup in Cleveland itself, like physical meetup or something, or?
Not yet. We're planning to. It's it's one of those things with I'm actually going to end the recording. Let me do that real quick.